Hi, my name is Bob Swanson. I am the lead online instructor for physical sciences and geography at Itawamba Community College. I work on the Tupelo campus, but I recently gave a Backyard Astronomy presentation on the Fulton campus entitled CSI Lower Stratosphere. Very exciting. So I'm going to try to replicate essentially what I did live for posterity. And what you're going to notice on the next two slides are a couple of videos to sort of set the scene. In early March of 2017, I had the great opportunity to fly with NASA's Sofia aircraft, the Stratospheric Observatory for Infrared Astronomy. And I flew into the lower stratosphere on that aircraft, and that aircraft, of course, houses an infrared telescope. So this whole talk is essentially a way of teaching folks about infrared astronomy, as well as sharing some of my experience aboard Sofia.
I'm sitting up, setting my sights to see the stars in a whole different light. We'll find a place to see much clearer in a tricked out plane with a 100-inch mirror. I'm loading up, taking my seat. Next stop is 45,000 feet. With visible and radio waves no longer cut it. No, the crew set up the scope, grab the flat door and shut it. I'm ready to head for the stratosphere. Sophia, spread your wings, take us out of here. Leave the rest of the atmosphere below. 'Cause I'm ready. Infrared, set to go. Cruising now, 8 miles high. The ioscope's a giant eye in the sky. It sees the cosmos in all its glory, with a wider range of waves than any other observatory. We'll check out comets, star death and birth, looking for planets just like planet Earth. Nebulas and galaxies that active only scratch the surface of just what Sophia sees. I'm ready to head for the stratosphere. Sophia, spread your wings, take us out of here. Leave the rest of the atmosphere below. 'Cause I'm ready. Infrared, set to go. We'll go through the top of the troposphere, straight to the stratosphere. We'll go. New discoveries dead ahead, observing an infrared go. Scientific and so futuristic, the view is exquisite and so terrific.
This is Paul Meltdown, so terrific. Is that a good
Sophia, spread your wings, take us out of here. Leave the rest of the atmosphere below. 'Cause I'm ready. Infrared, set to infrared, set to infrared, set to go.
And Sofia's right behind me. She's a flying telescope. So inside this aircraft we have a German-built 2.5-meter telescope inside a 747 SD aircraft. Now some of you may ask, how is Sofia different than Hubble or any other telescope that orbits? Well, Hubble is a type of marvelous telescope that has some capability, but it is limited. And so it's revealed what I'd like to call the crime scene. The capabilities of Sofia is to do infrared astronomy. What Sofia does is called spectroscopy. It's astrochemistry. And so the way I like to think about it is that it's doing the DNA analysis of those crime scenes that Hubble has found. We can look for carbon, water, hydrogen, oxygen, and different types of tracer elements that can tell us a lot about the universe. And that's how Sofia complements Hubble and other observatories that operate for the science community.
Okay, so if you watch those two videos, I hope I've sort of set the scene as far as what I'm going to be teaching about scientifically, which is infrared astronomy, and Sofia is part of the overall arsenal that NASA has in learning about the cosmos. And I like that analogy that Mr. Zavala uses of a crime scene, where when you step into a crime scene, you see the obvious stuff. You see the shell casings and the knocked over dresser and the broken glass. That stuff is easy to see. That might be what Hubble can gather when it looks out into the cosmos. But you also need to analyze the blood spatter, and you need to do a trajectory of the bullets, and you need to do DNA analysis of any evidence, and you need to do fingerprint investigation. All those things are some of the other tools you need, which in this case would be Sofia. You're looking at the same scene, and yet you're getting extra information by looking at it in a slightly different way, and that all helps to solve the case or to learn more about the cosmos. So that's the science. Now, educationally, what I'm also doing here is I'm introducing a thing called Nearpod. Here's the website, and you just register for it. There's actually an app that goes along with it. So I'm actually on my PC here showing you the Nearpod website and my library. Now, I've used Nearpod for a little while here, and so I've built a bunch of different lessons. The one I'm using tonight is called CSI Lower Stratosphere. And when you build one, you can either use a live lesson or you can do a student paced. Now, for my live lecture, I did a live lesson. So I'm going to go ahead and start up the live lesson. And when you do that, it generates a code. And anybody who has already downloaded the app, either to an iPad or to a phone, can actually enter this code, and now they'll be actively engaging in the lesson. Okay, well, hello there. So here's what it looks like on the iPad end now for your audience. So all they have to do is enter the code, FAIDV, and they join it. Now, it's going to download the session, and they're invited to put a name in there just to be able to identify themselves. And now they're actually live engaged with the lesson. And because it's a live lesson, we're going to step through it one slide at a time. But anybody who's now logged in, using an iPad or a phone, is now seeing this. And you're asking yourself, well, what is this? This is actually, well, it's an X and a dot, a dash, or a dot inside of a crosshair. So what do you do with it? This is to teach about the human eye and why we see what we see, and also why we don't see some things. So I used to do this using paper. I used to have these little slips that I would pass out at the beginning of a presentation, but shucks, you got iPads, you got iPhones. People could do this using their electronics at their location. So what you do is you look at this, you hold it out here, hold it at arm's length, and you close your left eye, and with your right eye you look at the dot, and you slowly bring the iPad or your iPhone toward you. And what you should notice is that the X disappears. Then you switch, and from that same location, close your right eye, and with your left eye, stare at the X, and you should notice that the dot disappears. So it's essentially a way of showing that we do indeed have a blind spot. Each of us has a blind spot. Doesn't make you a bad person. Don't let it affect your self-esteem. In fact, all vertebrates have blind spots. So you can ask your cat, your dog, your horse, your pig, your sheep, and they're all going to complain that they all have the same problem. And who does not have that problem? Your friendly neighborhood cephalopod, like a squid or an octopus, because their eyes evolved on a different branch of the tree of life than the vertebrate eye did. Now, if you wish, you can actually go into an explanation as to the physiological limitations of the human eye. The fact that light comes in through the cornea, through the lens, through the iris, and hits the back of the eye called the retina. And the retina, of course, is made up of these light-sensitive cells called rods and cones that turn light energy into electrical impulses, which then get fed along to the brain and make an image via the optic nerve. The problem is that where the optic nerve connects to the retina, there are no rods and cones. There are no rods and cones, and therefore that small area is your blind spot. Light falls upon that area, but that light is not converted into electrical impulses because there's no rods and cones there. Okay, so now that you've explained the physiological limitations of the human eye, it's time to move on to the physical limitations of the human eye. It turns out that when we talk about light here in the room is just the visible part of the overall electromagnetic spectrum. It's just a small sliver in what is all out there. And that's because the human eye can only see visible light. And so we are physically limited to what we can see. And of course, even the colors that we can see, Roy G. Biv, red, orange, yellow, green, blue, violet, the differences between those different colors mainly has to do with wavelength. As we can see here, red light has a long wavelength. Blue light has a shorter wavelength. And with those differences in wavelength, we also have differences in frequencies. So we would say that red light has a lower frequency, blue light has a higher frequency. So all these different types of colors of light all are made of all have different wavelengths, different frequencies. When you smush them all together, when you combine all the different colors, Roy G. Biv, the human eye sees white, which then leads into the next slide. So we move on to this slide and we say, well, gosh, I'm going to pick up the camera here. So here's white, right? You're seeing white. And the question is, well, what are you seeing? Well, you're seeing all the different colors. You're seeing Roy G. Biv, and to your eye, that looks like white. But what if we throw something on there? Now what's going on? Well, we're seeing Roy G. Biv from all of the screen except for where it says test. I did mention there was going to be a test, right? This test, we're seeing just red. So we're seeing red from here. We're seeing Roy G. Biv from everywhere else. And similarly, if we add on a green, if we add on a blue. Now, what happens if I take a filter? What if I take a little piece of, this is a gel here. What if I put a gel between the screen and the camera? And I'm going to put a red gel. What do you see? That's very interesting. Now what I'm going to do is I'm going to allow you to, well, I'm going to allow my audience to play around with a little website which will help them to investigate this a little bit further. Okay, so at this point now my students, I've advanced the slide on the Nearpod lesson, and they're going to see this page. And what they're able to do now is they're actually able to launch a little simulation. It's a PhET simulation from the University of Colorado to play around with visible light. I encourage you to use there's actually two options here. We're going to do a single bulb. We're going to do white light, not a particular color of light. Turn your flashlight on and you see that the flashlight shines into this person's eyes. I also suggest that you use the photon version of the light. So you're seeing all those different colors going into the person's eyes, which they then see as white light. And now what you can do to tie it into what we were just talking about is you can actually add a gel. So we're going to put a red gel between the person and the light source. And now all of a sudden they see red. Why do they see red? Because the gel only allows the red to pass. So this is just, and you allow them to play around, to discover a little bit. This is kind of a discovery learning opportunity. Once you've done this, then you show them the next couple of, actually the next activity now is to get them to explain what is going on. And so this is actually a slide that everyone winds up doing. And it says you've got a light source, here, you've got a piece of paper, a little bit of blue crayon, blue mark, you've got a red gel, and you've got a human eye. And you get them to draw what's really going on. And the cool thing is with Nearpod, you can actually draw. So I'm going to say, all right, so from the light source, of course, it's a white light source. It's producing all the different colors, red, orange, yellow, green, blue, violet. And it's hitting the paper. And of course, all those colors are being reflected. And I could draw all this out if I wanted to. Now, from the blue mark, what's important is that even though all the light is hitting the crayon area, the only light that's not being absorbed, it's actually being reflected, is blue. So where the crayon is, all the colors are absorbed with the exception of blue. With the white paper area, the important thing is that all the colors get reflected. And so all the colors wind up going, I could draw them all out if I want, just to red, yellow, etc., etc. The important thing to realize is that now you got blue light coming to the red gel, and therefore the red gel is not going to pass that blue light. It will, however, pass the red light that's coming from the paper. So therefore, wherever there's paper, you're getting red light going into the person's eye. And so what the person is seeing is red everywhere except for not red. So therefore, it just helps to understand what's going on here when you're viewing light through visible light through a gel. And again, it's kind of a neat little activity. The other cool thing is that the person can then submit. They can send their answer. Let's say confirm. I say yes. And now that shows up on the instructor's screen. So that, see how that just popped in there? And what I can do, and of course I would get a submission from everybody, and I can, first of all, I can inspect it as the instructor. I can say, well, gosh, that looks pretty cool. Let me take a closer look at it, and I get a closer look. I can also share it to everybody's, iPad. So now of course, this is the one that I work from, but there it is. And then I can unshare it and move on with the lesson. So I can close this little window, and then we move on to the next screen. And the next screen is just a discussion of the various filters or the various gels we've been using. And so I show them the transmission versus wavelength of the red filter. And as you can see, the red and orange end of the spectrum is what gets passed. For the green filter, it only passes the greens and the blues. And finally, for the blue filter, it doesn't pass the Roy G end of the spectrum. It only does the BIV end of the spectrum. But if you pay close attention, you'll notice that over here, each of these gels allows infrared light to pass. Go back. Notice that on that end of the wavelength, there's a lot of transmission going on, which then allows us to move into the discussion, getting us out of visible light and giving us the opportunity to talk about infrared light. Okay, so if you recall, we left off talking about infrared light. What the heck is infrared light? Here's where I encourage you to find a remote control. And in a lot of your classrooms, you'll have a remote control for the projector. And I encourage you to just start pointing it at your students or your audience and just pushing one of the buttons, volume button. Just push it a bunch of times. And point it at them and say, what do you see? And they're not going to see anything. But then use an iPad, use the computer screen. In this case, I'm going to point it right at this camera here. And notice what happens when I push the button a few times. You should see a flashing, right? So it turns out that the remote controls in your homes use infrared light to communicate from the transmitter to your electronics. So that's a type of light that physically we cannot see. And yet we can build stuff that can see it. So that's kind of neat. In fact, I can show off some other electronics. I've got a little photocell here. It's a photocell. And it's very much like the human eye. It takes light energy, converts it to electrical impulses, which then can be amplified by my little amplifier here. And maybe you can hear the little hum on my microphone. And so notice what happens. I'll just kind of set it down here. When I cover, you can see that it is indeed taking light energy and converting it into electrical impulses. Now what happens when I hit it with my infrared source? So not only does it pick up on infrared light, or visible light, but it also picks up on infrared light. Okay, and now that you have this remote control handy, to continue on the theme, now remember we talked about the fact that the gels all should transmit infrared light. Remember, on that end of the spectrum, in the infrared end of the spectrum, they would pass light. So you can test it. So you cover your camera, and you should be able to see some flashing. And that's true whether I'm using my red filter or my green gel or my blue gel. So again, so just showing that indeed infrared is a type of light and that infrared is able to pass through all these gels. Now another thing that's kind of cool that you can show off is the fact that just like, maybe you can see my reflection in my iPad screen here. It's just like visible light can be reflected, so also can infrared. Infrared, you should be able to, if I'm doing this, if I've got my angles right, you should be able to see some flashing off my screen. So that's very important because think about what a telescope does. Telescopes just reflect light. And so that's what Sofia does. It reflects visible light as well as it also reflects infrared light. Okay, and then one last thing, one last live little demonstration is I've got a bunch of wires here, and they're connected to a diode. This is actually a diode. It's an infrared diode. So again, if you held it up to your live audience, they're not going to see anything. And yet when you hold it up to a camera, what do you see? You should see light, right? You're seeing infrared light, which is kind of exciting. I wonder if we could hear that light. Remember how we heard using the photocell? We used this and we were able to hear the infrared light produced by the remote control. I wonder if we can hear this light. Let's find out. So I'm going to got my amplifier on. You hear the hum? Let's see what happens when I bring this photocell close to my infrared detector. That's my song. So what I've done is I've actually connected the whole thing to my iPad, and I'm playing Infrared Set to Go by Starman Bob Swanson and the same wavelengths. Okay, so I haven't forgotten about Nearpod. I've moved on to the next slide. And this is actually a good way of reviewing how much students have learned about these different terms like emission and absorption and reflection, that kind of stuff. So it's really just a matching thing. Again, you can use a pen, you can use a marker, you can type things in if you want. And if you make a mistake, you've got an eraser here. Again, I'm just going to make my little pen. Or my marker. I'm going to connect my partial transmission to the gel and reflection to the mirror, absorption to my black box, and emission to the sun. And again, if you wanted to feature, all these are going to come into the teacher's computer, and the teacher can essentially assess whether the students are understanding. And if there's one person who's really getting it, you can go ahead and feature them, make them feel a little special. Okay, so remember the whole idea here is that you need all these different types of light, and you need to collect this different type of light to really fill in the picture, to give you the whole crime scene. Well, why is that? Well, remember, here's my photocell. I'm going to pretend that that's like a telescope. Let's say this is my telescope, and here my diode is like a star. Now, would you agree that my telescope can see the star right now? Sure. Right? In fact, it could use visible light. It would be able to see the star. But what if I can do this with one hand or two hands? What if this was in between? If you were that telescope, could you see that star? No, you couldn't, right? Because you got something that's blocking the visible light from getting from the star to the telescope. But what if I was also observing an infrared? If I can do this properly. Notice that the infrared still gets through, even if the visible does not. So that's why using both of them to complement each other can really help to fill out the big picture. And here's a couple of examples of the same thing. So notice that all I see here is just a plastic bag. Well, that's because I'm using visible light. What if I looked at it using an infrared camera? Now I notice, oh, there's a toaster back there. So again, the infrared light, which has much longer wavelengths, is able to pass through the plastic bag, whereas the visible light did not. Same thing with this, it looks like a harmless rug here. but if I view using infrared, I can see what's behind the rug. Okay, so here's how could this be used in astronomy? Well, here's a good example. Here's Orion, a very famous constellation, Orion the Hunter. We see its belt stars, we see its sword. We're of course viewing in visible light, and we're seeing mostly the stars. The stars are pretty darn hot. They produce a lot of visible light. Of course, they produce other wavelengths as well, but a lot of these stars produce a lot of visible light, and therefore we see them this way in a visible light image. Notice, if I look at the same scene using a different type of telescope, if I look in the infrared, oh my goodness, there's so much more out there. In fact, what I'm really picking up on are these clouds of gas and dust from which new stars possibly could form. In fact, the neatest parts of Orion to look at is this area right in the Orion sword called the Orion Nebula. And at the heart of the nebula are 4 really hot stars called the trapezium. And through a visible, when you're looking through the visible, you pretty much just see the stars. And yet, in infrared, you see all these other stars back here. Normally, you would not see these using a visible telescope because the light from those stars way in the distance gets blocked by this huge cloud of gas and dust. But infrared is able to penetrate gas and dust much more effectively than visible light can, and therefore we see these background stars. So again, it's a way of filling out the overall crime scene by learning about stuff that we wouldn't be able to see in just visible imagery. In a similar way, then, if we look toward the center of the galaxy from our current position, which is out 2/3 of the way out on a spiral arm of the galaxy, in visible light, which is this one right here, you don't see very much because we're looking at so much dust. We're looking at so many stars as we peer toward the center of the galaxy. But if you look at it through different wavelengths, you can actually start to see objects there that wouldn't be visible in anything other than, or in just visible imagery. Okay, here's another application for infrared imagery. Now what we're looking at here are not just stars. We're actually looking at galaxies. These are entire groupings of perhaps 100 billion, 200 billion stars. In each of those little specks there, each one of these is a galaxy. So we're looking at, first of all, a huge field of view, but we're looking at galaxies that are pretty far away. So they appear to be relatively small. Now, why would infrared be so important here? Because if you know anything about Hubble's law, the farther a galaxy is, the faster it's moving away from us. And even if the galaxy, which is made up of stars, is giving off visible light, because it's moving so fast away from us, its light is going to be what's called Doppler shifted. And what's Doppler shifting? A little ball here. And if you ever had this experience, probably won't get picked up too well because I'm actually at the center of the sound. But if you ever had an ambulance come toward you and then go away from you, you notice that there's a change in the pitch or the frequency of the siren. When it's just stationary, of course, it just sounds like one single pitch. But when it is going toward you, the pitch shifts up a little bit to higher frequencies. And when it goes away from you, it shifts to lower frequencies. Notice all these galaxies are traveling very, very fast away from us. So if they're producing visible light, that light can get shifted because that light, the galaxy, the source of the light, is moving so fast away from us that it could shift into the infrared, in which case using an infrared telescope would be much more useful in viewing these distant galaxies. Okay, so hopefully at this point you're buying into the notion that yes, infrared astronomy is important, but why the heck would you put it in an airplane? Well, that has to do with the fact that if we had an infrared telescope at the surface of the Earth, it would do us absolutely no good, because the only type of light that gets through our atmosphere, notice this is a graph that shows the transparency of the atmosphere versus wavelengths on the x-axis. The only type of light that actually gets through the atmosphere is visible light and radio waves. Those are able to get through, the atmosphere is essentially transparent to that type of light. All other types of light, the atmosphere is opaque to. So that includes UV, it includes gamma, it includes UV, etc., etc. It also includes infrared. So if you're going to view in the infrared, you're going to either have to launch a telescope with a satellite, or you can also fly planes at high altitudes, which is where Sofia comes into play. Okay, so here's one more opportunity for students to use Nearpod to show what they've learned. So this is actually a star over here and your Earth, and you've got a cloud of interstellar gas and dust in between. And their task is to essentially draw what's going to happen to visible light versus infrared light. So I'm going to draw visible light. Of course, I know, because I've been paying attention, I know that visible light is a relatively short wavelength, and it's going to get absorbed or scattered by the dust. Whereas infrared, I know, has a longer wavelength, and therefore has a greater possibility of passing through that interstellar cloud of gas and dust and making it all the way to the Earth. So once they figured that out, of course, then I also throw in the fact that if you want to learn more about Sofia, I've actually got a YouTube page it's a YouTube channel called Stormin Swanson, StorminSwanson. And if you want to watch some of the videos that I produced while I was doing my Sofia missions, I encourage you to visit that channel. It's got its own playlist called the Sofia playlist.